Okay, so all right, so the last video, what we did was so one of the things that we wanted to show. Ooh, okay, I don't know. I could push the letters like that. Okay, one of the things that we wanted to show was that okay, so flat implied locally free, or over a local ring that flat implied free. And so one of the things that we needed to bust out doing this was this Tor functor, right? And what you did is, after tensoring up, you get to extend the exact sequence where you don't really know it's an injection, but the failure of the injection is measured by this Tor1. And so this is a derived functor, which I'm going to talk about today. Well, I'm going to talk about derived functors, and so it has some properties that we presented. In particular, if m was flat, then these things vanish, which proves that these things are exact. Notice that we're tensoring up with k, and in the last term is m, so that gives us that flatness, even though we're tensoring up with k, because the m appears in the Tor in this extended sequence, this long exact sequence. So yeah, so I'm going to now say a little bit about derived functors and what this was. So resolutions and derived functors. So we did a lot of cohomology in the previous semester. So, but we're going to come back to it now. Oh. Okay, so let's do some resolutions. So definition. So a left resolution. So let M be an R module. So this actually works in any abelian category. So one thing you have to worry about these things existing. Okay, so we're just going to assume they exist. So let M be an R module. So a left resolution, of M is so it's an exact sequence. And I'm going to write it in a kind of a funny way. So I'm going to write it P0 like this. And so I'm writing it with lower index notation. So maybe I can say a little bit about that. So we have this P2 ... like so. Is an exact sequence like this. So this is what a left resolution is. And if the PI are projective, so I guess I can put a 0 here. So it has to be exact. Are projective, then it is called a projective resolution. Okay, if the PI are free, it is called a free resolution. Okay, so you just have these things that do this. So one thing I want to note is that if we view these as complexes, so just kind of an observation, if we view these PIs, so this thing here, as a chain complex. So a chain complex is this is an exact sequence if we include this one. So I've written it a little funny, but if we view it as a chain complex where so let me write it like this. So the chain complex will be like this: P0, and then we'll put 0 here, P1, P2, etc. Okay, so a chain complex is this thing where d squared is equal to 0, and then they give you homology, right? When you take when you take the kernel mod the image, so if I took the kernel of this mod the image of the 2 map, then that would be the 2 to 1 map. So I would take the kernel of 1 to 0 and the image of 2 to 1, mod the image of 2 to 1, that would be the first homology. Okay, but if we view this as a chain complex, so we have, so given that it's a resolution, so that means that this is an exact sequence, right? And so what we'll have is we'll have H0 of this complex. So it's the image. So this is a good reminder. So this is the kernel of P0 to 0 mod the image of P1 to P0. And so this is just isomorphic to the original thing that we started, a resolution of M. Okay, and then HI of P bullet is equal to 0 by exactness, because the image is equal to the kernel. Okay, so the kernel of PI plus -1 minus the image of PI minus +1 to PI. So this is equal to 0. Okay, so we kind of took the exact sequence. So this was exact if I wrote it like this, and then we modified it. And so one way to view this is kind of like so you have like kind of a complex of one element here, and this complex maps to this complex, and they have the same homology. So this is a chain map of complexes, actually. All right. All right. Yeah. So so this is so all I'm saying is that this thing kind of encodes M. It's pretty much the same as M if you up to homology. If you view M as like the stupidest complex you can, where it's just in degree 0. Okay, so that's what a left resolution is. So similarly, a right resolution. So a right resolution of M is an exact sequence. Okay, so we'll do the same thing. So we'll do M0, I0, I1, I2, ... Okay. So it's just an exact sequence like that. That's all there is to it. And if the IJs are injective, so injective modules in our case, then the resolution is called an injective resolution. An injective resolution. Okay. All right. And similarly, the same remark applies, except for in homology notation or cohomology notation instead of homology notation. So if we view, so the same remark holds. Okay, so H0 of the complex here, where this complex here we're viewing as 0, I0. So it's almost an exact sequence. This is not an exact sequence. It's exact away from degree 0. Okay, this thing is isomorphic to M, and then the other HIs are 0 for I not equal to 0. Okay, so so maybe that's an exercise. Okay, maybe exercise here. All right. So, all right. So given these resolutions, we're going to use them to define our derived functors. All right, they're trying to troll me. Okay. So, so let's do. So yeah. So let's just do the derived functors here. Okay. So, so how do I define the tors? Okay. So maybe I'll define tors first. Well, let's see. Should I do derived functors first? Okay. So let's do. Let me just do. Okay. Let me do right. I'll do the most. Okay. I can't decide whether I want to do the more general thing or the um, or the example thing. So let's just do right derived functors. Or okay. So right derived functors here is so what you do is you take your object A. So you take A as an object. Then you take I, an injective resolution of A. And then what you're going to do is you take F as a functor. Okay, so to another, so I guess it needs to be an additive functor. So it just needs to be a functor which is valued in something where actually it needs to be a functor to an abelian category, and does it need to be additive? So it needs to be a functor to an abelian category, and I'm not exactly sure what the hypothesis here. I'll look this up. What the most general hypotheses are here, but I'll give some examples. Okay, so this needs to be to an abelian category. Okay, and then you can think about what makes this work. So then what you define is you define RF, so the right derived functor, so definition. So let's say the right derived chain complex. Let's say cochain complex of A is this thing. So we're going to do R F of A. And so it's going to be defined to be the chain complex where you just take F and you apply it to I. So in other words, right, so we're just going to do, so in other words, what do we get? So we'll have F of I0. So this is 0. This keeps going. So this is degree 0 here. Then we have F of I1, F of I2. Okay, and the idea is that this functor here is going to mess up the sequence from being exact, right? But it's still going to be it's going to be a chain complex because d squared is equal to 0, and that just comes from functorality. So if I apply the map twice, it's going to give you 0. Okay, and then so this thing here is a chain complex. Same thing. This is I want to say cochain complex, because I'm doing cochains because of the indexing. So indexing goes up in cochain complexes, and then it goes down in chain complexes. Okay, and so the ith right derived functor of F is this functor. So RIF of A. So this is defined to be the ith cohomology of this complex. Okay, so all right, so that's what we have here. Okay, so the amazing part about this is that this doesn't depend on the, so amazing fact. Okay, so this doesn't depend on the choice of injective resolution. Okay, so that's a theorem. Okay, so yeah, so you take an injective resolution. So a left-derived functor is going to be very similar. So so let's do left resolution. So okay, so let's just do, okay, I'll do it down here. So it's going to be pretty much exactly the same thing. Okay, so maybe the first example. Okay, so the first example to give of this one here is that if you take so take f to be mod r, I don't know, b dash, like this. Okay, so what do you do? And so then you take a, right? And then I take some injective resolution for a. Well, okay, let me just say this. R, F, R, RI. So these are the X functors. Mod R B blank here of A. So this is defined to be equal to X I B A. So these are things called the X. I don't know what they're extension functors. Okay, and it turns out that like these things, so so like why the heck do we care about these? So x1 of BA. So these things parameterize equivalences of extensions of B by A. So it's like this.
So when I hear extension, I'm thinking like base change. Is that the idea?
No. These are a little bit different. So
Okay.
it's like how can you build out a middle thing built out of the two outside things? Like so it's almost like, okay, so you know, not every exact sequence is split, right? And so how many ways are there to make non-split exact sequences out of A and B, right? So that's the kind of the question, right? So a split exact sequence would mean that E looks like A direct sum B, right? And so you know, there's other exact sequences that you can do where the two factors on the end are still B and A, right? And this thing here, this group, is all the isomorphism classes of those. So it turns out they form a group, right? And there's a group structure on these exact sequences, and they're all captured by this group. Okay, I guess I'll say more about this later. Okay, so these are the X functors. Okay, all right. So let's do some left-derived functors. Left-derived functors are like our Tor ones. So left-derived functors. Okay, so it's going to be the same recipe, right? So we're going to take an object. A is an object. Okay, and instead of an injective resolution, we're going to take a projective resolution. So this is a projective resolution. Excuse me. Okay, projective resolution, and then we're going to take F to be a functor. Okay, and Okay, so let's give the definition. So what we'll do is we'll take this. So we'll do the same thing. So we'll take this chain complex here. So we'll take P0, P1, P2. Okay, and then we apply F. Okay, and so away from the zero piece, this thing's exact, right? And then after applying F, it may not take injections to injections or surjections to surjections, right? And it gets messed up, right? So we apply F and we get a thing here. Okay, F0 needs to be 0. That's one of our properties. Okay, and this keeps going. Okay, so now this thing here is a chain complex. Okay, so this is a chain complex. So this is this chain complex here. And we call this thing the left-derived chain complex, LF, excuse me, LF of A. Okay, so the left-derived chain complex for A. Okay, it appears to depend on the projective resolution, but again, this is going to be another thing where it doesn't. Okay, again, this isn't necessarily exact at 0. It maps to A, and then that maps to 0. Okay, so we have this thing, and so this is the first part of this. Okay, so 1 is this, and then 2 is that the left-derived functor. So the ith left-derived functor of F, sorry, applied to A is the homology of this complex. So this is, and we use the notation Li F of A. And so this is really, this is the, so okay, this is what it is. And let me just put this in parentheses. So what are you actually computing? You're actually computing F of P bullet like this. Sorry, HI F of P bullet. Okay, so this is a notation for this. And so again, there's this magical fact. So like we said before, there's amazing fact that this doesn't depend on the choice of injective resolution. This doesn't depend on the choice of projective resolution. So let me kind of wrap this up, okay, nicely. That's the definition of this. Okay, so amazing fact. So this doesn't depend on the choice of projective resolution. Okay, actually, it's also amazing that it's a functor, right? So these are actually, so 1, I guess this is 2, and this is actually a functor, right? So given a morphism from A to B, right? Then you have to take 2 resolutions. Think about this. So you have to take 2 projective resolutions, one for A and one for B, do this crazy process. But it turns out that you get maps from Li F of A to Li F of B. Okay? Okay, and through this crazy process. So this means that we're going to have to somehow cook up maps between the complexes. Okay. Also, let's say this too has the two amazing facts, right? This is a functor. Okay. So let's do Tor now. Okay. So the main example here was X, and maybe this shouldn't be so small. This is like a really big example. So this is the X groups. Okay. So this is super important. These X are the right derived functor here. They also can be defined in terms of taking a projective resolution of, so there's another way of defining this, and that's by doing a projective resolution on this component, right? Or let's see, on this other component, and then applying A to that sequence, and then taking homology. So like there's a lot of things which seem like they depend on lots of choices, right? But everything ends up being well defined, and it's like a homological algebra thing. So it's like a up to homotopy thing. Okay, so so the main example. Okay, here is these are the Tor functors. Tor IR, let's say M and N. Okay, so what do we do? How do we define this? Okay, so what we'll do is, so how do we define this? So what we need to do is we first take a projective resolution. So so we can do either a projective resolution of M or a resolution of N. It turns out to be well defined. So what we'll do is we'll take M. Okay, so let's take a projective resolution. M0. Okay, so here. Okay, so we have this thing here, and all right. So this is a projective resolution. So then we kind of like we chop it off here, right? So projective resolution again means that this is an exact sequence, but we chop it off, right? And we only consider this chain complex now. Okay, 0. So it's no longer this part's exact. And so this is only a chain complex after chopping, with where the H0 here is M essentially. Okay, so all right. So now what do we do? So now we apply one of our functors. Okay, so what we're going to do is so we resolve with M. Let's take the tensor product with N. So we do P2, N, P1, N, P0, N, and then this goes to 0 like this. Okay, so now we have a chain complex. So it was exact. So this thing previously, this thing was exact over here. So exact means that it has 0 homology. So the image is equal to the kernel. The image of the previous is equal to the kernel of the next. But after applying this functor, if it's not flat, it's not going to take injections to injections necessarily, right? That's one of the issues that we had with things that were not flat. So at this step we apply this functor. Okay, and then what we do is we take homology at each stage. So here so we'll do HI of this complex P bullet tensor N, tensor over R with N, and this thing is defined to be equal to Tor R I of M N. Okay, so this is the definition here. So the definition of Tor. Okay, equivalently, okay, this is a big theorem. Right? It's a homological algebra theorem that we could have taken resolution. We could have done this in a different way. Have taken, okay, so a resolution of n. So let's do, we could have started with n, okay, 0, and then we'll do, what do we want to call it? Let's say p, let's do p, okay, maybe I'm going to regret this, doing all these primes. Okay, so we could have started with the projective resolution of n, okay, and then again, we truncate this part, so we only consider it as a complex. Okay, and then we apply a functor. So we apply the functor. Okay, so we're applying m now. Okay, and we get the 0 functor. And so now we have this chain complex. So this chain complex, this is the chain complex. This is the left-derived chain complex of this thing, m, applied to n. Okay, so this is this. That's the name of this chunk. Maybe we could have put a bullet here, but this is the chain complex we get. And what is this literally? So this literally is p. So we replace n with a resolution, and then we tensor it up. Okay, and if we were to do this, then we taking homology of this, p bullet prime tensor over r with m is equal to, well, this is Tor Ri and m as well. Okay, so this is the other way of defining Tor.
All right, so we have that these these Tors are these HIs, and we know that the HIs of the projective map is 0 when it's exact, and so when the Tor is 0, that was like a, oh, that's what you're saying. It's like a measure of like failure or flatness or something.
Yeah, exactly,
like when it's
exactly. Like
okay.
So we knew that this thing was exact up to the previous part, right? And so if the higher Tors vanish, right, then that means that the thing was flat, right? Because it preserves the injection. So we know it preserves surjectivity automatically, right? But if m were flat, right, then this thing would still be it would still be an injection, or it's still so do I want to say if it's an injection? So it would still preserve limits, right? So yeah, so it would make it so that the homology would be 0.
Cool. Yeah, because I kind of piecing that together from the definition of these of the homologies and the okay. All right. Cool. Cool.
Yeah.
Thank you.
Yeah. That's exactly that's exactly the point, right? Is that the it measures the failure of homology. One thing that we can do, we can start to try and compute the first ones for all these. So let's try and do that. Okay, so let's do an example computation. I mean, so yeah, so maybe we can write that out. So lemma. if m is if m or n, if either m or n is flat, then tor tor r I mn is equal to 0 for I greater than or equal to 1. Okay. All right. So let's do the proof. Right. So what we'll do is so what we can take an injective resolution. So we'll do it for one case. So let's take an injective resolution of m, or projective resolution. Right. So here, so you have m0, p0, p1, p2, etc. Okay. And so so what do we have here? So then we tensor this up. So okay, so then we drop it to just this chain complex here. Okay, so we drop this piece up to here. Okay, and then we tensor up. Okay, so by definition so how do I turn this into so here's a question, is how do I turn this into an exact sequence, right? So we know that this isn't quite exact, right? Okay, so what we have to do to make this an exact sequence is we truncate. So this is not exact, right? But what we can do is we can just replace this term with the image P1, and then we can do the image of P1 here. Okay? And if we do that, then this is an exact sequence, because we know that the image of this is the kernel of the next one, and now we know that the image of this is the kernel of the next one. So this one is exact. Okay? We also know that, okay, so now we'll tensor up like this. So this is an exact sequence, so it takes exact sequences. So n we suppose that n is flat. M P1 to P0. Okay, and so this goes to 0. So this is also exact, right? And so now we have, if we take the homology of this sequence, okay, so let's start with H1. H1 of P bullet tensor Rn. Okay, so this is equal to the kernel of this thing. Okay, this maps to the image of, and so this is actually the same thing as the kernel of the previous map. Okay, so this is the kernel of this modulo the image of P2. And then we have, this goes into P1 tensor Rn. This is a P1. Okay, and so the kernel here is actually the kernel of the previous one. Okay, this is, so we know that this is 0 because of exactness. Okay, and so I claim that this is the kernel of this, the P0 image. Because it factors, because they, okay, so why is this the kernel of this thing the same? Because the map factors through, so this factors through this inclusion. So the image of Okay. Okay, so this is Tor 1. Okay. And actually the same thing holds for the higher ones. And it's actually much easier because you don't have it you don't have to truncate. Okay. I guess one thing we maybe don't need to worry about is this thing, the image injecting into the other one. But since n is flat, right, then we injections go to injections, so we can view this as inside the P0 if we want. Okay, so yeah, so that's why we can replace this. Okay, and that's Tor 1. Okay, and so similarly for the higher ones, we'll get Tor I, this thing here, m is 0. Okay, it has to do with the n being exact, and then it just takes this exact sequence to an exact sequence. Okay, so yeah, so in the previous time we showed that that Tor 1 being 0 was the same thing as flat, right? So in the previous class, so previously, so we saw Tor 1R. So if we had this and m is equal to 0 for all m, so this implied that n was flat, right? And to do this, we needed the short exact. So we needed this short exact sequence to long. So this thing used a short exact sequence to long exact sequence. Okay, so that was that. If you had so again, if you, so this was like something that was super useful, was that if you had n to a to b to c, a short exact sequence, right, then you get an associated long exact sequence. Okay, and how do you get the long exact sequence, right? So, or what does the long exact sequence looks like? So we had something like this. So the surjections are preserved. Sorry, B tensored up to NR, A tensored up to N over R, and then this thing continued, right? And then we had Tor 1 R C N, right? And then we had Tor R1 BN, and then it continued with the higher Tors, AN. And this came in and it went around, and this was Tor 2. Okay, and so what's going to happen here is that this thing here is going to come from this comes from a map of cochain complexes or chain complexes. Comes from an exact chain complexes. Okay, maybe I can say a little bit about this. Let me remind you while we're here. Let me just remind you what this means. Okay, so this is a property we talked about a long time ago. Okay, when and so it said that if what happened? Okay, so it says that if so if we have chain complexes, so if A, let's say if A to B to C is a map of chain complexes, is a map of chain, is a short exact sequence of chain complexes. So meaning, so this means at each level, right? So this thing is exact. Okay, and then I usually work with homology, so hopefully I get this right. So so what we'll have is we'll have H0, A. So we get, so whenever you have a map, a cochain map, so a cochain map, so to have a map of chain complexes, what you do is you get, so okay, for what does it mean to be a map of chain complexes? So it means that, okay, so the map of chain complexes part means that this diagram here, oh, where'd it go? AI plus 1, BI plus 1, if this is the D's, right, and this is the map FI plus 1, so that this diagram commutes, so that you have this, so this is a chain, what's called a chain map. All right, and then chain maps, anytime you have a chain map, it induces a map on the homologies. Okay, so it turns out that chain maps of complexes give you maps on homologies. And then, okay, so if we have a bunch of chain maps, and it turns out that the chain, that they're exact, meaning that horizontally they're exact, right? Then what happens is you get one of these, right? So from H1 of C, H1 of B, H1 of A, and then it keeps going like this. H2 of C, okay? So what do we need to do in order to prove this thing? Okay, so we have this general, so this is a general theorem from homological algebra. It's just about chain complexes. And so we have this one about tors here. And so what we need to do is we need to look at the complexes here, right, for each of these things, and then somehow get chain maps between them, right? Get a short exact sequence of chain complexes. So if you can get a short exact sequence of chain complexes, you can get this. So okay, so I guess next time I'll do some more computations with extens tor. In particular, I guess we should compute the zeroth one. The zeroth one will actually just return the functor. Yeah, and so I guess we'll do more on that.
Sweet.